Give me one moment. Okay, let's get started. So today we'll go over, I guess, Euler phi function and Fermat theorem, and then we'll probably do a bunch of questions from the book for practice. Yeah. Okay. So sorry, let me disconnect my pencil. Okay, so we have the Euler phi function. So this is a function phi from n to n, such that phi of 1 is 1, and phi of n is number of positive integers m with 1 less than or equal to m less than n, such that GCD of mn is 1. So these are like all the numbers between 1 and n that are co-prime to n, right? And we had an example that the units, like the multiplicative group, so this is shorthand for z mod nz cross, right? This has order phi of n, right? Anything co-prime is invertible, and anything not co-prime is not invertible. So really quickly, we have the result that given any given group G and G, G to the order of G is what? What is this? Here. Okay. So what does Lagrange theorem tell you? What's the order of G? What does Lagrange theorem say? So recall Lagrange theorem is it's E, but Lagrange theorem, the order of G, which I will, some books write it like this, some books write it like this, right? It divides this, right? So we could write this as, order of G times K, but by definition of order, G to the order of G is E, and E to the K is just E, right? So this is just E. So knowing that, we have Euler's theorem. So let n bigger than 0, GCD of AN is 1. So in particular, this means I guess class of A is in U of n. then what do you know? You know A to the order of U of n is E, right? That's what we just did right here, right? Any element to the order of the group is E. So this is under multiplication, right? So, but what does it mean in U of n case? This means what's the order of U of n? It's phi of n, right? So a to the phi of n. And in this case, equals means congruent, right? Congruent to an identity of U of n is 1, right? Mod n, right? So this is Euler's theorem, right? If you raise any element in U of n to the phi of n power, you get 1, which is the identity. So a corollary is in U of p, right? In z mod pz, remember, phi of p is p minus 1, right? So you have Fermat-Little theorem, which is pretty much a corollary of Euler's theorem, right? It's a to the p minus 1, because in this case, phi of p is p minus 1 is congruent to 1 mod p, right? And this is for p prime. So in this case, p doesn't divide a is the same as GCD of a and p is 1, right? Because p is prime. And you have furthermore, if you multiply by a on both sides, you always have this identity for any. This might be a bit harder to prove, but for non-coprime things, but you can show this. Okay, is everyone clear? All of this is just a result of the thing I have in blue. It's just Lagrange theorem. Yeah. So any questions? If not, I think it's best we do problems in the book. Yeah. And then call it a day. Okay. So let's do some questions from the book. So I have the book with me. I don't know. Let's do 8. Use Fermat-Little theorem to say p equals 4n plus 3. Right, so it's 3 mod 4. It's prime, sorry. Then what? Then there is no solution to x squared is congruent to negative 1 mod p. Then there is no solution to negative 1 mod p. Yeah. So without loss of generality, we can assume x is not divisible by p, right? Because if x was divisible by p, x is congruent to 0 mod p, and 0 squared is clearly not negative 1. So clearly x has to be coprime to p, right? It's some number between, I mean, it's represented by some number between 1 to p minus 1, right? Okay. Everyone good so far? So what does Fermat-Little theorem say? What does Fermat-Little theorem say? So again, let x be such that p does not divide x, right? Because if it did, it's congruent to 0. So Fermat-Little theorem says what? X to the p minus 1, right? This is Fermat-Little theorem, is congruent to 1 mod p, right? Now, what is p? P is 4n plus 3. So x to the 4n plus 3 minus 1 is congruent to 1 mod p. Now this is x to the 4n plus 2. Now what? So what do you know? So let me write it like this, just to give you all a hint. What do you know about x to the 4n? What is that? So again, maybe let's do this. Suppose x squared is congruent to -1 mod p. Yeah. Let's derive a contradiction. So if I assume this, what do I know about x to the 4n? Yeah. Let's get a contradiction. Suppose for by contradiction, there is a solution. So what's x to the 4n if x squared is congruent to -1? Connect it. How about this? Let me give one more hint. This is x to the 4 to the n times. So if x squared is congruent to -1, what is x to the 4th? It's x to the 4th is congruent to 1, right? I mean, if you have this and you square both sides, it's going to be congruent to 1, right? So x to the 4th, p, but that means this is just x squared congruent to 1 mod p, right? And that's a contradiction, right? Because we had x squared congruent to -1 mod p and x squared congruent to 1 mod p. You can't divide by p and have two different remainders for the same number, right? So contradiction. Everyone clear so far? Everyone see how? So this is just an application of what do I call it? Yeah, an application of Fermat theorem. So we'll do some problems on cosets later, but let's move on. Let's do maybe Lagrange or let's do problem 1, the easy one. So suppose G is a finite group with element G of order 5 and element H of order 7. Why must order of G be bigger than or equal to 35? This should be immediate. So let me remind you. So Lagrange. If H subgroup of G, I mean, this is part of Lagrange, but order of H divides order of G. So how can you use that? This should be quick. So you have an element of order 5 and an element of order 7. So like apply Lagrange somehow. So how do you convert elements? So if G and G is order 5, what's the subgroup generated by G? This has order 5, right? I showed this last time, right? And if H and G is order 7, order of H is 7, right? So in particular, order of this by Lagrange must divide order of G, but this is 7, and 5, which is, the subgroup generated by G, must divide order of G. That's 5. So order of G has to at least be 35, right? Because 7 divides it and 5 divides it, right? At least. Wait, is everyone good so far? This is just Lagrange theorem. Okay, let's move on. Let's do something harder. Let's do something with orders. Let's do 16, yeah? So 16, if order of G is 2n, if order of G is 2n, what is it? Proof number of elements of order 2 is odd. Number of elements of order 2 is odd. So again, let's do contradiction. Assume number of elements of order 2 is even. Does anyone see how to approach this? What is so special about elements of order 2 compared to like elements of bigger order? So if I give you a group, can you divide it? Can you divide it up? Do you, like if I give you an element G, like can you, right? So given group G, I can divide it up, right? Divide it up, right? I can order it in pairs. Order in pairs, right? In what pairs? Well, if I have G, what do I know must exist by group law, the third group law? What must exist? So given G, what's the third property of a group? What must I have? So there's associativity, identity, and what's the last one? So there's the inverse, right? So I can pair things up based on G and its inverse. Agree? Now, in general, G might not be equal to G inverse, but ren is G equal to G inverse. Is G equal to G? Other than, of course, other than identity, right? So identity, identity is just super nice, but ren is G equal to its inverse. I think I showed this. Yeah, I certainly did. When I did dihedral group, remember with rotation and reflection? Reflection was order 2, and you got, what's the inverse of a reflection? Yeah, it's itself, right? So in other words, when is G equal to G inverse? When G is order 2. So I could pair things up, right? So I have order of G, which is 2n, which is even, minus, so we assume number of elements of order 2 is even. So this is just what? So number of elements of order 2, right? So these have, it's are its own inverse, right? And this is even by assumption. We even by assumption. So even minus even still even, right? And then we subtract off subtract off identity, right? Subtract off 1, right, for identity. And then the rest are not order 1, not order 2. So they're pairs, right? They are pairs there. I'm grouping them in pairs. So this is, elements, number of elements of order bigger than 2. And these are in pairs, right? So this is even, right? And that's it. And that's all I have, right? I should get 0. But this, because that's all the elements G can possibly have. But this is a problem, right? Because 0 is not odd. Yeah, this is even, this is even, this is even, this is odd. Even minus odd is odd. And so it can't be 0. So we have a problem, right? So contradiction. So number of elements of order 2 is odd. Everyone clear? So again, the idea is I group elements based on G and their inverse. So these are always even, right? It's right here. They come in pairs. So it's always even, right? No matter how many you have, because a number times an even number is still even. And then if I assume number of elements of order 2, in which case I count the pairs once. If the number of those is even, then when I subtract off the identity, I can't have 0 equals an odd number. Yeah. Everyone clear on this? So this is just a fact about elements of order 2, right? Because if G squared is 1, you multiply by G inverse on both sides, right? You get G equals G inverse, right? So, okay. And any questions so far? I don't want to do too much problems. Okay. So let's move on. What problem should we do? Let's do something with cosets, yeah? Yeah, let's do 17. Suppose recall cosets, right? GH is the set of GH for H and H, right? And G to H is number of, I'll do left. Yeah, there's a theorem that says number of left is equal to number of right, but number of left cosets. Distinct, yeah. Left cosets of H. And recall 2 cosets are equal, right? G1, G2. If and only if, there are many equivalent definitions, so you have to look it up in your book. But if and only if you multiply by this is in H. Yeah. So moving on. So we have from problem 17, G to H was 2. So there's only 2 distinct left cosets, right? And if A and B are not in H, show. So A is not in H, B is not in H, show AB is in H. Okay, so this thing, what does this mean? The number of distinct left cosets is 2. And remember, the cosets partition G, right? So you have G is like H union another coset. Let's call it GH. You always have H, right? H itself is the identity coset. And then we only have 2, right? So G is H union, this distinct, they're disjoint. So let me do disjoint union, right? Since they partition G. So I could write like this because there's 2, right? So if it's 3, then it's H disjoint union G1H disjoint union G2H, right? So on, so forth. Okay. Is everyone following so far? Yeah. So this is a question on cosets. Great. Now, if A is not an H, what is AH? So AH is a left coset, but there's only 2 distinct left cosets. So if A is not an H, which left coset is it equal to? Can this happen? Can AH be H? So I'm asking, is AH equal to H or AH equal to GH? Which one is it? You have two choices, right? I mean, there's only 2 distinct left cosets, so you'll have to choose. So which one would? So what does the first one mean? If AH was equal to H, using this property, right? So what 2 cosets are equal if and only if when you multiply by the inverse, it's an H, right? But in this case, my G2 is just E, yeah? The inverse of E is just, so then A E inverse is an H. But this means A is an H, right? Because E inverse is E and A times E is A. So this can't happen, right? Because we assumed that A did not belong to H, right? So it must be the latter. Yeah. Everyone agree? Everyone follow? Hopefully, I'm not confusing any of you. I know we went over closest last time, but last week actually. But so okay. So AH equals GH means AG inverse. Sorry. Do I want to do? Sorry, it's inverse on the right. Okay. G inverse A is in H. Yeah? Everyone clear? Now, let's assume by contradiction that AB was not an H. Then same exact argument, right? ABH must be GH. Agree? Because, again, this coset has to equal H or GH, and it's not an H, so it must be equal to GH. So G inverse AB is an H. Now, why is this a problem? Can anyone tell me? I have this element is an H, this element is an H. What does that force B to be? Can any of you see it? We're missing like one last step. What can you tell me about the element B from these two? B is not E. No. So how about this? From this, G inverse AB, I'll write little h, right? It's some element, yeah? So let's multiply by G inverse A. The inverse of this, right? I mean, I'm just going to write like that. So B is G inverse A inverse times H, right? This is this element's in H. Okay, now H is in H. From here, G inverse A is in H. But if G inverse A is in H, H is a subgroup, right? So it has its inverse, right? The inverse belongs to H. So this whole thing is in H. That would mean B is in H, right? Because H is a subgroup. It's closed under the operation, right? And that's a contradiction because we assumed B did not belong to H. So, everyone good? I mean, from your response, right? B doesn't have to be the identity, right? I mean, in fact, it can't be the identity from what you see here, because H is a subgroup. Yeah. So if B is not an H, it can't be E. So, everyone understand? Everyone follow? This argument really only works because we know A and B sort of belong here, right? If the index was not 2 and larger, it could be like A belonged to G1 H and then B belonged to like G2 H, and like things don't work well. So, any questions? Everyone follow? Okay. Yeah, this one's a bit hard. So I think you will have to think it through. Like cosets at the beginning can be a bit difficult to understand. Yeah. Okay. So knowing that, let's do another example on cosets maybe. Yeah. Show additive group of real numbers have infinite index in additive group of complex numbers. So again, we have C under plus, this is a group, and then as a subgroup, normally they do this, but since I wrote C on the left, I think it's like this, right? Bigger than or equal to R under plus, that's a subgroup of C under plus. Now, we want to show the index from C to R is infinite, right? So what does it mean to be infinite? So here it was 2, right? In which case there were 2 different cosets, right? So here we want to show there's infinitely many, right? So again, a coset, I'll do left. Yeah, a left coset is, again, is of the form GR, right? I mean, from above it was GH, right? But H is R in this case. It's the set of GR for R and R, right? And G belongs to given where G, for some G in complex numbers. So to show it's infinitely many, let's figure out what it means for 2 cosets to be equal, right? equals G2R. If these two are equal, again, by equivalently, it means G2 inverse G1 is in R. Agree? I'm using the blue underline, or I'll box it. I'm using this, right? So two cosets are equal if and only if G2 inverse G1 is in R, right? Everyone follow so far? So far I just wrote definition, what it means for two cosets. Okay, now what does this mean in our case? What's the operation here? So what's dot in this case? What is the group operation? So, you know, you should always go back. So dot means plus, right? And what's the inverse of a number under plus? Like, what's the inverse of like 5 under plus? Like 5 plus what number gives 0? Should not be that bad, that hard. So it's going to generalize the complex numbers, right? Like the inverse of I, it's still minus I. Yeah. So dot means plus, inverse in our case is, the minus, right? Because again, our operation is this. It just means this, right? So i.e., I prefer to write it like this. Okay. So question. If I subtract two complex numbers, when do they belong when do they equal a real number? So if G1 is complex, right? A plus BI, G2 is C plus DI. I need this to be in R. What does that mean? That means what? The I part has to go away, right? So does everyone agree that B must equal D for this to be a real number, right? Because if B is not D, it's complex, right? It's not real. It has a non-zero I component, right? Okay, but then we're done, right? So two cosets are the same. Two cosets are the same if the representatives have same imaginary part, right? But then you're done, right? Because the elements IR, 2IR are all different, right? Because they have different imaginary parts. So you see you have infinitely many, right? I mean, these don't need to be all of it, right? You have 1 plus IR, but this is enough, right? That this is infinitely many different cosets, right? Because again, if any of these two were equal, they would need to have the same imaginary part, which certainly is not true. Everyone clear? Hopefully that makes cosets a bit more understandable. So I trust you all. So okay, let's do like one last thing. So prove or disprove every subgroup of the integers has finite index? So this should be very simple. What are the subgroups of the integers? I think this was in the book, or you had to prove it, maybe. So question, are the integers cyclic? Yes or no? Are integers under addition, generated by one element? So subgroups of Z, I guess a cyclic group, it means it's generated by one element, right? And integers are generated by one. Yeah, you can get every integer by powers of one, right? Like -5 is 1 to the -5th, right? Because 1 inverse is -1, and raising -1 to the 5th power means -1 plus -1 plus -1 plus -1, right? So you see that integers are cyclic. So, and you know that subgroups of cyclic groups are cyclic. That's a theorem in the book. So all subgroups of Z look like, subgroups Z. So I guess they want proper subgroups here. So subgroups of Z look like, but yeah, all subgroups are proper. DZ for D an integer. So again, these are all finite index, right? Like Z mod Z is just E, right? Z mod DZ. This is just, remember, we learned this, right? These are remainders when dividing by D, right? Dividing by D. And now you sort of see why we use this notation, right? Because if I call this, H, right? If I call DZ equal to H, right? What does it mean for G1H to equal G2H? It means G2 inverse G1 is an H, right? But this means, again, we wrote before, G1 minus G2 is an H, but this is DZ, right? So this just means the difference of the two numbers is a multiple of D, right? And that's exactly how you checked, right? If like in our like Z mod 7Z, how do you check the class of 1 is equal to the class of 8, right? It's because 8 minus 1 is multiple of 7, right? So you sort of see why we use this notation now. Once it's just coset. It's the coset with the group DZ. Yeah. So anyway, yeah. So all subgroups are finite index. Yeah. So does everyone understand so far? Okay, great. Let's call it a day today. Yeah. I'll announce the quiz on Wednesday. So no problem. Stop.